Section 7.4, we're going to do two different activities. One is to find arc length, okay, so the length of an actual arc. And then the other one is to find the surface of revolution. So we've done solids of revolution, right? We're finding volume, the space inside of some kind of an object, and the surface of revolution will be the surface area of that same object. All right, so we're going to start with arc length. So you guys know how to find the length of something that would be straight, like linear, right? You got distance formulas. Those are fantastic ways to do that. But it doesn't work extraordinarily well if you're doing the length of a curve. So arc length is found by using an integral. And if you take a look at this, it can be defined either in terms of y or of x, just like the others that we've been working with for your solids of revolution. And you see that you've got a square root. You've got the derivative squared underneath that square root and a 1. And can you see embedded in there a distance formula? Right? The distance formula is when we take the difference in y values and we square them, the difference in x values and we square them, when we square root the whole quantity, that whole sum. So you've got the distance formula embedded inside of this formula. What does what? That works really well if you're working with polar coordinates. S equal r theta. But we're not always working in polar coordinates. But you're welcome to take Calc 3 or 4. One of those has polar coordinates in it. Then you take physics and you can do that too. Yeah. All right, so the other thing about S equal r theta, you can correct me if I'm wrong, isn't it on a circle specifically? Can you guys remember? Or is it any arc?
Sounds right. We're talking about a uniform circle.
Yeah, and see, we're working here for any kind of an equation, so I don't think it's going to work really well for that. We do use polar coordinates in one of the other calculus classes, though, and we do talk about arc length there as well.
Yeah, I was immediately thinking S equals S naught, but V not a T.
You guys and your physics. Okay, we're going to find arc length for this curve, and if you take a look at the formulas for these, the way in which we find these is pretty straightforward. So if we're dealing with a function that's defined in terms of x, like f of x equals, we're going to use the second equation. If we're dealing with a function in terms of y, we're going to use the first one. So I think I might have actually slipped those in there in the wrong direction. Yeah, I think I copied and pasted them wrong. So these are backwards. Just make that note in your notes that I had these written in here backwards. That's what happens when you're moving things around trying to make them show up right. These are reversed of where they should actually be on here. Yeah, so either change where x equals g of y and y equals f of x, or just change the integrals. Okay, so if you've got it determined by y equals f of x, you're going to have your arc length determined by the function that's got the f prime in it. And if you've got it in terms of g of y, you've got it in terms of the one that's got g of y in it.
So if y equals blank, it'll be f and x.
Well, okay, so I think that I'm not trying to complicate things, but if you take a look at this particular function, you'll notice it's set up as y equals. So we're not going to try and solve this for x. That's not what we're doing. We're just going to take the derivative. Okay, so it's already written in terms of x. It will stay in terms of x. Everything on my antiderivative will be done in terms of x. Okay?
So it's d of x.
Yeah, it's dx. Exactly. Okay, yeah. So what we're going to do is we're going to take the derivative of this guy. So what's the derivative of x to the 5th over 10? Well, 5x to the 4th over 10, and then it will reduce, right? This other piece, though, this is 1/6. Don't go moving my 6th. But this is x to the negative 3. So what will this piece of the derivative be? Okay, so 3x to the negative what? 4th over the 6th that's already there. Okay, so I'll take one step to just kind of clean them up as you guys were reading them already, some of you. So this is x to the 4th over 2, and then I have minus, and then I have 1 over 2, x to the 4th. All right, we can work with it from this perspective. That's okay. I'm going to actually show you how to work with things with the negative exponents as well, though, because I think that actually makes this problem a little bit easier. You'll notice both of them have a 2 in the denominator, right? So I'm going to pull the 1/2 out in front because we can sort of factor that piece out. And if you'll notice, this is x to the 4th minus x to the negative 4th. That's actually fairly friendly. So the formula that we're using is the one with the f prime of x, and it's this one right here. So what we're supposed to do is we're supposed to take that derivative that we just found, and we're supposed to square it, add 1 to it, and take the square root, and then integrate. So I'm going to set all those pieces up. We've got our integral, and it gives us our limits of integration. It says 2 to 5, so we've got that piece. And then we're supposed to take the square root of 1 plus. So this is 1/2. And then I have x to the 4th minus x to the negative 4th. And all of that's squared dx. Okay, is that okay? Any questions about the setup, where pieces came from or anything like that before we start working on the integration itself? Okay. We need to square what's underneath that radical and add 1 to it. You have a question, Caleb? You look like you have a question.
Well, no, I figured the square's gonna change. For some reason, I thought when we integrate, it's gonna become the original.
No, it won't. Yeah. Because we've got the 1 plus more than anything. It'll be not because of the square, but it'll be because of the 1 plus part that will change. Yeah. Okay, are you guys ready to get started? Here's some cool stuff about this particular one. We've still got the integral from 2 to 5. We've still got the square root. I'm not going to have to deal with that for a little while, and I've got the 1 plus. Obviously, if I take the 1/2 and I multiply it by itself, I have 1/4. If I have, and I do have, x to the 4th minus x to the negative 4th, and I multiply that by itself, what am I going to get? Well, the first piece is x to the 4th times x to the 4th, which is x to the 8th. Oh, that's good. What happens when I do the inside terms and the outside terms? Yeah, they become 0, right? So I've got x to the 4th and x to the negative 4th. That adds to x to the 0, which is 1. So one of these is, I think, are they both negative actually? So do I have negative 2 in the middle? Yeah. So each of these become x to the 0, which is 1. That's a 0 up there. That does not look like a 0. It looks like a... And then the other one here is also 1. So and they're both negative. So we have negative 2. And then my last terms are plus what? X to the negative 8th. So inside here I have x to the 8th minus 2 plus x to the negative 8th dx. It's the same thing. Because that 1/2 is multiplied by the stuff that has the addition and subtraction in it, we can apply the squared to each of those pieces individually so that we get the 1/4. Yeah. I'm just using a new screen. Give me a sec. Okay. Now what? Yeah, we can multiply the 1/4 through. I think it might be easier for us to combine that 1/4 with the 1 at the beginning for the moment. So let me show you something kind of neat that's going to happen here. So this would be 4 plus the x to the 8th minus 2 plus x to the negative 8th, and it's all over 4 and underneath the radical. Okay, so I'm distributing the 1/4 through the second piece, and I'm getting a 4 over 4 as my first fraction. Wouldn't which one be 5 over 4?
Did we just combine one?
We got a common denominator, like that. Is that okay? Okay, common denominator gave me a 4 at the beginning. Here's something kind of cool. Square roots. You can't just distribute them to every piece, right? I mean, like I can't take this and say I want the square root of 4 plus the square root of 8 x to the 8th plus the square root of negative 2. I mean, I can't do that, right? But between the numerator and denominator, I can. I can take the square root of the numerator and compare that to the square root of the denominator, right? Well, that's kind of nice because what's the square root of 4? 2. So my denominator can actually be pulled out from underneath the square root as a factor of 2 in a denominator. So I can rewrite this so that I have a 1/2 in front. I've still got my integral from 2 to 5 of the square root of 4 plus x to the 8th. You know what? Let's actually combine these pieces. There's no reason not to. This is x to the 8th. I've got a positive 4 and I've got a negative 2. So that's going to give me positive 2, right? Plus x to the negative 8th dx. It's looking a lot better, isn't it? Yes, it is. And here's the nice thing about this one at this point. That's in parentheses, factors. So let's see if you can think about how it would have to factor. And in order for it to be useful as a factor, it would have to factor into itself, right? Two pieces that are identical. What would the first terms be in those sets of parentheses? X to the 4th. What would the last terms be? Yeah, x to the negative 4th, right, Kaylin? So x to the negative 4th here. Good. What's going to need to go between them, though? Plus. Check this out. This factor, right there, not factor with that value right there, isn't it pretty much the same thing as this one? What's the only difference? The sign in the middle, right? Whether it's plus versus minus. So the only effect that that has is that instead of having a negative right here like I have on these two, I have a positive on these two.
Which were you looking at?
I'm comparing it to the original one that I squared. I had the original piece, the derivative, exactly, yeah, that I squared. And that's exactly the same thing as this one, except that it's got a sign different in the middle.
Is it worth it to do that step, or could you just take the antiderivative, but it's all under the square root?
The only way you could take that antiderivative is if you had a u substitution to be able to deal with it. And that's a problem, because you don't, right? If you let the denominator underneath, or not the denominator, but what's underneath the radical be u, you don't have a du in the problem. So it is necessary to do that step. And it's kind of cool because now I don't have a radical either, do I? I just have x to the 4th plus x to the negative 4th dx. Because I have the square root of something that's squared. Right? What's the square root of x squared? Well, it's x. So what's the square root of x to the 4th plus x to the negative 4th squared? X to the 4th plus x to the negative 4th. Nice, nice, nice. We're almost done. So this is 1/2. What's the antiderivative of x to the 4th? X to the 5th over 5. What's the antiderivative of x to the negative 4th? Good. And we're supposed to be evaluating this at 5 and at 2. So I have a 1/2. I have 5 to the 5th over 5. That's lots of 5s. Minus, and then I've got 1 over 3 times 5 to the 3rd, right? And then all of that, I've got to do the same thing with the 2. So I have 2 to the 5th over 5 minus 1 over 3 times 2 to the 3rd. And of course, everything in that bracket is multiplied by the 1/2 that's at the beginning. So grab your calculator, simplify that out for us. I think a decimal answer or a fractional answer will work on this one. I don't think it repeats anything because I've got 2's and 5's in denominators. That's kind of what I have to have for no repeating decimals is 2's and 5's in denominators. So in either the fractional or the decimal notation. Somebody tell me what you get when you simplify it all.
I bet 309.32.
Let's write out all the decimals. Can you try again for me, Abby? I think it gives you exactly 4.
Oh, 3195.
And then, of course, if it told you to approximate, we would. Did anybody see what that fraction is, just for fun?
How big was it?
618,639/2,000.
Yeah, good. All right, so either of those are versions of the correct answer in exact form, without approximating or rounding anything. Okay, any questions on that one? Now here's the kicker. We were able to do that all by hand, right? I mean, you have the calculator, and you could use the calculator for some help for some things. Not all of these problems have the ability that when you square the derivative and you add 1 to it, that you will be perfectly able to factor it into something that's a square of what's underneath there and then take a square root. Not all of them are going to have that ability, right? And that should make sense to you. It should look like that was sort of very friendly how it worked out, right? So I want to do an example of one that doesn't work out so friendly, because the directions actually tell you how you can get around the fact that it's not going to be friendly. What part of the directions here? With the help of a graphing utility. So when you see that phrase in your homework on WebAssign, it's telling you you're going to have to use a calculator to do it. It's not going to be able to factor nicely and take the square root of it. It's just not going to work, okay? So use that sort of as one of those clue into the direction pieces. That means I have to do this with the calculator. So we're going to do all of the setup, though, before it. Yes, we are still going to do the setup before it, Levi, I promise. Okay, so what was the first thing that we had to do in order to use either of those formulas for arc length? The derivative. So this is actually like x to the negative 1. What is the derivative of x to the negative 1? You're thinking about antiderivative. We want derivatives. Negative x to the negative 2 or negative 1 over x squared. Either version of those, right? Okay, so if we're taking a look at this one, and it tells us that we're going from 1 to 3, the square root of 1 plus, and I'm going to leave it as x to the negative 2. It doesn't really matter which one you use, but we're going to put it in our calculator here in a minute anyway. It's a little bit friendlier to use negative exponents than to use fractional ones. What did I mess up on?
Negative x, negative 2.
Oh, yes. I didn't leave it there. Thank you. Is it going to matter?
No.
It's actually not, because I'm going to square it here in a second, but I will put it in there correctly. Thank you for correcting me. All right, so yes, ma'am.
Well, I mean, it's getting squared again, but because it's squared and you're taking the square root, I mean, obviously you have to combine terms and stuff first. But if you didn't have the 1, then wouldn't it matter?
If you didn't have the 1, squaring and square rooting are inverse operations, but because it has the 1 plus, you can't just sort of eliminate them. It's not
Right,
able.
but if you didn't have the 1,
Mhm.
then wouldn't the negative matter since the square root and the
Yes,
square root?
that's true.
Okay.
It would. Yeah, it would. And you encounter that when you hit things with complex numbers, which we aren't doing calculus with complex numbers, but you're correct. Yeah. All right, so I have 1 plus what? X to the negative 4th. All right, so let's talk about why I need my calculator to do this. What part of this makes this something that's not going to be able to factor into itself squared? There's a couple of things when you look at this that you should know. I can't factor this. There's what? The negative exponent is not a problem. We had a negative exponent on the last one actually as well. It's not the negative exponent. Although we don't typically do a lot with them when they do have negative exponents, but that's not the kicker on this one.
Doesn't have a middle term.
It doesn't have a middle term. This isn't a trinomial. It's a binomial, right? And And if you'll remember, the only way you knew when you were factoring back in, algebra somewhere along the way for factoring binomials was differences of squares. And differences of squares, even if they worked, would require a negative between these two. There's not a negative between these two, there's a positive. So this doesn't even factor at all, much less factor into two pieces that are identical. Yes, you get to leave it that way, and your calculator gets to help you. Are you guys ready to see how to use your calculator to do a problem like this? Here's the cool thing about this too. What I'm showing you, because you have to use it on this problem, means that you could use it on the problem before to check your answer, right? And that's cool too. Agreed? I always like to be able to use my calculator to make sure I got the answer right. So grab your calculator. I want you to put this square root part underneath. Everything right here in this very last step is going to go into y1. Okay?
Literally do that.
Are we putting the square root in there as well?
Yep, we're going to put the square root in there as well.
And we're on
We're just going to put the square root of 1 plus x to the negative 4. Very much glare over there. I think that's okay. I'm going to show you two ways to do this. And I know those of you who had me for Calc 1, we talked about this once upon a time 6 months ago or something like that, but just as a reminder, I'm going to show you how to do both forms of them. Okay, so one form leaves the screen, so just exit the screen. Actually, both of them need to leave the screen. So we're not in the graphing screen anymore. You're just in the plain old regular screen of the calculator, the one where you add your grocery list together or whatever to make sure you have enough money. That's the screen, okay? All right, so what we're going to do is we're going to hit Math. And if you go down far enough, you'll see Math 9, and it says FNINT. Ever see that? That stands for function integration. And if you hit yours, it might look like what mine does. It might not. It might put a script S. Does anybody have one where it actually puts the script S? Okay, so I'm going to borrow Levi's calculator. Promise I'll go back so you can see the differences in those in case you have that version. So let me do mine first. Okay, here's the notation. Who has one that looks like mine? Kaylin and Hannah. Okay. Here's what you do next is you're going to tell it vars. So that vars key, you're going to go over to y vars. It's a function and it's y1. So you're telling it my function is what I stored in y1. You put a comma and you tell it x. X is my variable. You put a comma and you tell it the lower limit of integration, which on ours was 1. And you put a comma and you put the upper limit of integration, which is 3. So this tells the calculator I want the area under this curve, basically, because that's the formula we're using, of the y1 function where x is the variable between the x values of 1 and 3, and you hit enter and it gives you your answer. Now I'm going to use Levi's. If you have one that looks like this, you actually put it in much like what it looks like on your actual paper right now. So you put a 1 here and a 3 here. You could actually type in the function right there, and that's okay. You can do that. But I wanted to be able to show you something else later, so we put it into y1. So I'm just going to put y1 right there, because I already stored it in y1, at least in theory. Did you store yours in y1, Levi? It's there? Fabulous.
Yep.
And the x here tells it dx. Hmm?
Y bars.
Yes, bars, y bars function. Yeah. And if you hit enter here, I should get the same answer that mine did. Oh, good. That's a relief. Both of them say 2.146622 ... forever, right? Okay, so we don't have an indication of how many decimals we're supposed to be using, so let's just go with 2 for now, but just make sure to follow whatever the directions WebAssign or the directions on the homework paper or whatever you're working with tell you. So we'll go with 2 on this one. So my area, my arc length, which is little s, I want to show you one other way to do this too. But s, little s is what they use for arc length, would be approximately 2.15. Okay, is that all right? Wow. If anybody needs a calculator, Levi's got 2. Okay, let me show you one other way to do this, which is kind of fun and cool. You guys ready to see it? Okay. In your calculator, you already had y1 put in, correct? Yeah? Everybody put it into y1 because it actually has to be now for this, for what I'm about to show you. Okay, I want you to graph this function. So we're going to hit window, and we're going to go just a little bit beyond the window we care about seeing. So this one, we're supposed to be going from 1 to 3. So maybe you go from 0 to 5. Okay, something just a little bit bigger than 1 to 3. So I'm going to make mine go from 0 to 5. And I really do want to see some negative and positive values. So I have no idea if this is going to be a good one or not, but I'm going to do negative 5 to 5 and just graph it and see if I see enough of my curve. Oh, that looks pretty good. Okay? So is everybody good with that? We're pretty okay with that screen. All right, here's what I want you to do now. I want you to hit second, trace. And you get this calculate menu. Second, trace. Do you see number 7? Number 7 should look appealing. Looks like what we're doing. Lower limit. What's the lower limit of the integration we're working with? 1. So just type 1 and hit enter. What's the upper limit? 3. So type 3 and hit enter. How cool is that? You can actually see the shading. All right, and it gives you the answer on the bottom, just like it did on your other screen. Here's something about this. You have to be in the window that shows 1 to 3, or it won't give you an answer. So if you use some random window that's not the one you were expecting, it won't actually give you an answer for that. But this is pretty cool, right? 2 different ways to do the same thing. All right, we have one more problem we're going to take a look at today. You guys ready?
That one's my favorite.
That one's your favorite? Oh, I'm so glad. I made you all go, today. One of those fun moments, yes. Okay, surfaces of revolution. The formula for these looks almost like the ones we were just dealing with. Let y equal f of x have a continuous derivative on AB, and S, this is capital S now, is the area of the surface of the solid of revolution. Okay, so the solid of revolutions that we were doing before, but now we're doing the surface area of them. All right, do you see pieces that look similar? We got radicals, we've got derivatives of, or squares of derivatives. We've got 2 pi in the front, right? That comes from the rotating factor, like our cylindrical shells. Yeah? And you see r of y, that's like the radius we were doing before, yes? Radius. It tells you r of x or r of y is the distance between the axis of revolution and the graph of f of x or g of y. Okay? That's what we were doing before, which must mean that this is something akin to the height, right? The square root of 1 plus and so forth is akin to the height of what's going on. So we didn't really have to look at the graph to do arc length, right? You just took the derivative and you moved on. But you're going to have to look at the graph on this one, or you're not going to be able to figure out what r of x or r of y is, right? So we're going to be drawing that representative rectangular region just like we were when we were doing solids of revolution on this. Shall we give one a try? Sorry, people are still writing. I don't want to leave my screen just yet. Okay, let's take a look at one. This is y equals the square root of 9 minus x squared from negative 2 to 2. Ignoring the negative 2 to 2 for a moment, do you know what this is a graph of? It's a half circle. This is a semicircle. It's the top half of a circle. Yeah? Think about it if you squared both sides. Y squared over here, and then you had 9 minus x squared on the other side. X squared plus y squared equals 9, which means it's a circle of radius 3. All right, so either because you graphed it in your calculator or because you thought through it like we just sort of verbalized out loud, this is a semicircle. Okay, I'm pretty okay with that version of it. And it goes from negative 3 out to 3. And up to 3 as well. But I'm not actually supposed to go from negative 3 to 3. I'm supposed to go from, negative 2 to 2. So my region will not be the whole half circle. Okay, so that's the region that I'm supposed to be rotating. And it says in the directions around the x-axis, so like this. All right, so r of y, how is it defined? R of x or r of y is the distance between the axis of revolution and the graph. So what is the distance between the axis of revolution, the x-axis, and the edge of this graph? It's just y, right? That's the distance. It's how far out we would go. And I didn't draw my representative rectangle. I think that's what Evan was trying to tell me, actually. Sorry about that. Let me get that drawn in. There we go. Yeah, perpendicular, like you said. Okay, so that radius is y. And we have our function. It's the square root of 9 minus x squared. So what in the world will my derivative of that be? Plain old-fashioned chain rule, no logs in it or exponentials. What's the derivative of the square root of 9 minus x squared? To the negative 1/2, and then what? Times negative 2x. Okay, can we clean this up some? Sure. We're going to get x on top and the square root of 9 minus x squared on bottom. And it's negative, yes, thank you. Okay, so that's my derivative. So this is the f of x derivative, so f prime of x is what this is. And then r of x, that is the radius, is actually y. That's what we just said a moment ago, right? And what is y? Well, square root of 9 minus x squared. So these are the two pieces that we actually need to be able to do the surface of revolution. So capital S, that looks funny, equals the integral, 2 pi first, times the integral from what to what? Negative 2 to 2, right? Or if you read it from top to bottom, 2 and negative 2. And it's supposed to have r of y, or r of x next, which is my square root of 9 minus x squared. And then I'm going to have the square root of 1 plus this derivative that I found, which was negative x over the square root of 9 minus x squared, all squared, and then dx. It does, but you know what? No, we don't get to use our calculator. It's going to clean up so fast, you're going to be like, whoa, how did that happen? So just hold tight for just a second. Let's actually square what's underneath there and see how this all does, in fact, clean up. So we're going from negative 2 to 2. I've got the square root of 9 minus x squared on the outside. Over here I've got the square root. I've got 1 plus I've got x squared on top. What is the square root of 9 minus x squared squared? Okay. Hang on, I've got it. Go to my next screen. Okay, so what would I do next? Yeah, I would find a common denominator. Very good. So this square root of 9 minus x squared, that's totally fine. Over here, I'm going to have to do this times 9 minus x squared. And on the bottom as well, right? So I'm going to get the square root of 9 minus x squared, and then what? Plus x squared over 9 minus x squared. Now what? Nathan, you're grinning at me. What's going on next? Okay, so what's in the numerator at the moment of that last piece becomes just 9, yeah? So I've got a square root of 9 minus x squared. I've got a square root of 9 in the numerator, and I've got a square root of 9 minus x squared in the denominator if I separate the square root between the numerator and the denominator. And then what happens?
Lots of things cancel.
Just like that, right? What's the square root of 9? It is, it's 3. So this is the integral from negative 2 to 2 of 3 dx. Don't stop in too soon.
From -2 to 2, or -2 to 0?
You're going to go from negative 2 to 2 because you're spinning this around the x-axis. If you're spinning around the y-axis, we would only go from 0 to 2 because we'd get the other half of it when we do the spin.
Well, I meant like sometimes you have to do a 0 between, because it cancels out.
Oh, not here. What you're thinking of is when it crosses the x-axis, where some of it's below and some of it's above.
I did.
Yeah, you didn't have to. If you did, it wouldn't have hurt anything, I don't think. But all right, so what's the antiderivative of 3? Huh? Just 3x. Evaluated at 2 and negative 2. So this is 6 pi x. I don't know why there's a dx on the end there because I got carried away, I guess. And then there's my 2 and my negative 2. So what am I going to get when I plug in 2? 12 pi minus a negative 12 pi for a grand total of 24 pi. And it does make sense that those two pieces are 12 pi. They're equal because this is a graph that's symmetric, right? The area from negative 2 to 0 is going to be the same as the area from 0 to 2. So that's why you're getting those two pieces of 12 pi being the same. All right, any questions on that? All right. Yeah.
So the 2 becomes 6x times 2 pi, so it'd be 12 pi.
Mm-hmm.
And then if you plug in negative 2, you get negative 6 times 2, which is that negative 4.
Yep, that's what I've got right here.
Oh, minus, okay.
Yep, and then the minus is because of the fundamental theorem of calculus.